Alright, so this is our equation that we're going to use for universal gravitation. Hopefully you already have it written down in your notes. If not, here it is. Pause the video now and look at it. But we're going to do some sample problems now that involve this equation. Alright, so here's you and your girlfriend or boyfriend. You're both sitting by each other. You love each other. You each have a mass of 60 kilograms. You're sitting about 20 centimeters apart. And I know that's probably a lot farther than most of you actually sit with your boyfriend or girlfriend. But we can talk about that later. I want you to calculate the gravitational attraction force between the two of you. So there's not only an emotional attraction, there's a gravitational attraction. So let's calculate that. These problems are going to be the same as any other problems we do. It's just going to be the guess method. As long as you know what you're given, what they ask you for, and be able to plug it into the equation, you're pretty much going to be okay. The tough part with the gravitation equation is that there's going to be a lot of scientific notation that you use, and I'll show you a little bit exactly how to enter those numbers into your calculator. Alright, but here's our givens. We know that both of the masses are 60 kilograms. It's say that you each have a mass of 60, so mass 1 and mass 2 is going to be 60 kilograms. I know the gravitational constant is 6.67 times 10 to the negative 11. That's a given. That's never going to change. And the radius, or the distance between the two of you, r in this case, because of the gravitational equation, is 20 centimeters. This says 0.2 because we can't leave it in centimeters. Remember, distances always have to be in meters. So to convert from centimeters to meters, you move the decimal 2 places to the left, which gives you an r of 0.2. And you know you're looking for the force of gravity. So here's our equation. And all we need to do is plug our stuff into here and solve it. Alright? I'm going to show you how to enter this correctly into your calculator to make sure you do it right. Alright, so here are the numbers that we're going to need to enter into the calculator. And the most important thing to remember with scientific notation is that you need to know where the parentheses go. Make sure that that entire scientific notation number goes inside the parentheses. So I'll do 6.67 times 10 to the negative 11th, and to do scientific notation in these calculators, I would go second x to the negative 1, which gives me that capital E, remember, and then negative 11, close the parentheses. And then since all of this is multiplication and division, I can do it all at one time and only hit it once. You don't have to do that. In fact, it may prevent calculator error if you don't do that, but you can, as long as you enter everything correctly. So I'm going to open the parentheses again and put a 60, multiply by 60 again, and then I can just divide straight by 0.2 squared. Hit enter, and we get 6 times 10 to the negative 6th. And there you go. Alright, so that's the answer you should have gotten. Here was the work. Here's the answer, 6 times 10 to the negative 6 newtons. And with these problems, we're not ever going to worry about directions, because remember, this is an attractive force between the two of you. The same force going one way is the equal force going the opposite way. So positives and negatives are never going to really come into this stuff. Alright, you can pause the video a minute, and I want you to do this second sample problem and see what you get. Alright, let's see what we're given. We know the mass is 55 kilograms, our mass. We know the moon's mass is 7.4 times 10 to the 22 kilograms. Those units are both okay, so we can leave that. Gravitational force constant. And we know that the radius of the moon is 1.74 times 10 to the 6th meters. I want to stop right there and ask you a question. Looking at my handy dandy old-fashioned piece of paper again. I want to know why we needed to know the radius of the moon for this last one. Because if this is me standing on the surface of the moon, what is the distance between me and the moon? Because that's what r is, right? That's the distance between the two objects. Well, obviously, this distance is 0. So if this is my equation, g mass 1 times mass 2 divided by r squared, and r equals 0, the question is, what is the gravitational force? Well, if you plug 0 in for this and hit enter in your calculator will kind of tell you that you're an idiot, because it'll say something like syntax error or something like that, because if you put 0 in the denominator, that's actually undefined. We're not sure if that's 0, or if it's infinity, or what it is. But obviously there is a gravitational force of attraction here. If you stand on the ground outside, your distance between you and the earth is 0, but there's still a force of gravity. And that's where the concept of center of gravity comes into play. Because you have a center of gravity that's usually pretty close to your waist, and the earth has a center of gravity that is obviously at its center as well. So the distance that needs to be measured is actually not at your feet, but it is at your center of gravity, which usually we neglect the difference in this distance because it's very negligible compared to the distance between here and the center of the earth. So the R, the distance that would be measured, is actually between your center of gravity and the earth's center of gravity. And for practical purposes, we really just consider the radius of that planet to be the distance that we enter into the calculation. So that's why we need to know the radius of the moon. All right, so there's our numbers. There's our equation. Plug our numbers into the equation and multiply them. And it's very, very important, and notice that this is the way it is. It's very important that, first of all, that you remember that there's a squared on the R in the denominator, but secondly, that when that distance is in scientific notation like this one is, that the squared goes outside the parentheses. If this squared is inside the parentheses in your calculator, what you've actually done is just squared the sixth. Let me show you. You see if I do 1.74 times 10 to the sixth, and then I put that squared into the calculator, all I've done is square that sixth. But that squared needs to be outside the parentheses. All right, so to find the force of gravity, remember our G was 6.67 times 10 to the negative 11th. One of the masses was 55, and the other mass was 7.4 times 10 to the 22. Getting small out there. And then we had this radius of 1.74 times 10 to the sixth, and we're going to square that. In the calculator, here's how we would do it. We can do it all at once as long as we do everything correctly. 6.67 times 10 to the negative 11th times 55 times 7.4 times 10 to the 22 divided by 1.74 times 10 to the sixth, close the parenthesis, put the squared on the outside, hit enter, and you should get the right answer. That should give you 8.97 times 10 to the 1, or 89.7 newtons. Rounded off to the correct significant digits, that's 90 newtons. So that's the answer that you should get. Once again, if you square a number in scientific notation, make sure that the squared goes outside the parentheses. One more common mistake that I want to show you. If you look at number 2 on the homework, and I'll do some of those problems here as well, you'll see that the distance given was 7.5 times 10 to the 5th kilometers. All these distances, just like any other distance we have, need to be converted to meters. All right, and normally when we convert to meters, we go 3 places to the right. Right, and we could do this with this one as well. Actually, it's not 7.5; it's just 7 even times 10 to the 5th. You could do that with this as well. You can put 7 and 5 zeros on it, and then throw 3 to the right. You throw 3 more zeros on that. That's correct, but it's a lot of writing that I don't really like. If we move the decimal place 3 to the right, what we've actually just done here is added 3 to this exponent. So this number actually becomes then 7 times 10 to the 8th meters. Right? So in other words, if you're going to move the decimal to the right ordinarily, all you have to do is add that same number of places to the exponent. And if normally you move the decimal to the left, all you have to do is subtract actually that same number of places from the exponent, right? So we move the decimal 3 to the right, that's the same as adding 3 to that exponent. So this converted to meters would be 7 times 10 to the 8th meters.